So today, inshallah, we are going to work a simple example for a projectile. In this projectile, we are going to learn how to create a body again, review what we did before, and we are going to learn new properties for the body. So basically, we will learn how to set the mass properties and how to set the initial velocities for a body. Also, we will review how to rename entities so we can understand better how to rename it, and we will practice that. We will also focus on what is called the hierarchy. So we will try to understand how the things are arranged in atoms. We will again run the interactive simulation, and we will have more details, a little bit more details about the simulation time and the step size or the number of steps. We will create again measures for different characteristics of the motion, and also we'll look at some dynamic characteristics, and we'll try to relate those dynamic characteristics to the physical movement of the projectile. We will look at the post-processing in the animation. We will study this widget in details, and then we are going to look at more graphics, add more graphics on the system. So we'll learn how to create box and how to place this box, and how can we change the appearance or the graphic properties of those boxes. In order to make our model more realistic, we'll try to create contact force between the projectile body and the ground body. So we'll learn how to pick different solids and how can we set up this contact model between the bodies. We will talk about the measures and how can we send the measure into extended graphics or extended plots, and then we learn more about the post-processing plotting in atoms. So this will be our lecture today. We are going to start by reviewing the theoretical part of our particle. Before, right? Okay. So what we are going to do actually is to draw the free body, the body, and then draw the free body diagram for this body. So I'm going to assume the particle is moving within a coordinate system like this. This coordinate system x and y. Assume our coordinate system starts, or particle or projectile starts from the origin right here. And this projectile will typically has initial velocity v naught. This initial velocity will have certain inclination angle with the ground or the horizontal x-axis. Let's call this theta. What we learned before is that this projectile is going to fly in parabolic motion. So we would like to find the equation that will give us this motion. In order to find this equation, we draw the body in general position and identify everything on this general position. So the particle in a general position will be like this. It will be flying with velocity component in the x, vx. This is v of t. It will have component in the x, vx, and component in the y, vy. At any time, the position of the projectile will be described by the distance x and the attitude y. So I would like to find the velocity and the position of this projectile. In order to do that, we would draw the body and the forces acting on this body. So I have the body is right here. The forces acting on the body is only the weight, mg. The body is moving. It has displacement x and displacement y, like this. And at every time it has certain velocity v. The body started from the origin, so I can say x of 0 is equal to 0 and y of 0 is equal to 0. The body started with initial velocity v naught. This v naught can be decomposed into a component in the x, vx naught, and vy naught. So I can write down vx naught is equal to v naught cosine theta, and vy naught, which is at time equal to 0, is equal to v naught sine theta. Now this is the body, these are the forces acting on the body, this is our coordinate system, and those are the initial conditions. Now in order to analyze this body, I need to find out what are the physics that will govern the motion of this body. This body is moving under the effect of gravity, external force, with initial conditions. So in order to derive the equation of motion for this system, I have to write down all the physics involved. Fortunately, in our case here, all what we have is a dynamic motion for our projectile. The dynamic motion will have Newton's second law, which says sigma forces equal to mass times acceleration. This particle, as you learned before, the particle is described by its motion in displacement rectangular coordinate systems. Now we don't have any rotation, that's why we don't add the rotational Newton's equation. This is a vectorial equation, and our particle is moving in two directions only, planar motion in two directions, x and y. So I can split this equation into two scalar equations. Sigma forces in the x direction equal to mass times acceleration in the x direction, and the sigma forces in the y direction equal to mass times acceleration in the y direction. If you look at this body, in the motion in the x direction, we assume we neglect the resistance of the air. So there is no resistance for the motion in the x direction. And there is no forces acting on the body in the x direction. So I can write this equation 0, no forces. And what is this? This is the mass. And what is the acceleration in the x direction? The acceleration in the x direction is the second derivative of the displacement. I have the displacement in the x direction is x. So the second derivative will be x double dot. And for the y direction, if you look at the forces acting on the y direction, I have only the effect of gravity. And notice the effect of gravity is in the negative y direction. This is our positive y. The weight is in the negative y. So I will say the forces that I have is minus mg, equal to the mass times acceleration in the y direction. The displacement in the y direction is y, so the second derivative will be y double dot. So I can write it like this, y double dot. So now you have the first equation of motion and the second equation of motion. And as you can see, those equations describe the accelerations. So I can, from the first equation 1, I can say x double dot, which is dx second derivative of x, is equal to 0. And from the second equation, m can cancel with m, so I can say y double dot, which is equal to actually dy squared d2y by dt squared is equal to minus g. So those two equations describe the kinematics of our body. The acceleration in the x direction is 0, the acceleration in the y direction is constant. But what we are interested in is the velocity and the displacement. So in order to get the velocity, we integrate this equation. So if you integrate both parts, you will get x dot of 0, x dot of t is equal to x dot of 0. And if you integrate this equation, you will get y dot of t is equal to minus gt plus y dot of 0, the initial velocity. And this will be equation number 5 and 6. And then I integrate it again, so I will get the displacements. I will get x of t is equal to x dot of 0 times t plus x of 0, and y dot of 0, y of t y of t is equal to, the integral of this would be minus 1/2 gt squared plus y dot of 0 t plus y of 0. And this would be equation 7 and 8. Those two equations describe the motion of our projectile. Now all what I need to do is basically substitute the values of the initial velocity and the initial displacement, because we have the body started from the origin. The initial displacement x and y are zeros, so this term is 0 and this term is 0. The initial velocity, I have initial velocity in the x direction, which is this value, and I have initial velocity in the y direction, which is this value. I will substitute them and rewrite my equations. So I will have the x of t is equal to the initial velocity in the x direction, which is v naught cosine theta multiplied by t, and the y of t, if you substitute the initial velocity here, is v naught sine theta. So you will get 1/2 gt squared plus v naught sine theta t. So for the displacement, I have the displacement of the x in the x direction is linear, increasing with time, and starts from 0. The displacement in the y direction is this parabola, and this is what you have seen like this. The shape of the parabola will depend on two things. Number one, the value of the gravitational acceleration and the initial velocity in the y direction. How about the velocity? As you can see, the velocity in the x direction, vx of t, this equation will be v naught cosine theta, and as you can see, it's constant. How about for y direction, vy of t is equal to what? This equation. So it will be minus gt plus v naught sine theta. I am going to assume this is equation number 9, 10, and this is equation number 11 and 12. So now when we analyze the motion of the projectile, we'll be interested in the velocity and displacement. If we look at the velocities, those two equations describe the velocities, those two equations describe the displacement. So if you look at the velocity in the x direction, if I would like to plot these velocities, I'm going to plot them against the time. So how do I plot a function? In order to plot a function, basically you will identify time steps where you would like to calculate the functions, and then at every one of those time steps, what you are going to do is to substitute into this equation. So assume I'm going to run this projectile until, say, for example, 2 seconds. So I will assume I'm going to start from time equal to 0. This would be, say, 0.5 second. This would be 1 second, 1.5 second, 2 seconds, 2.5 seconds right here. And then we have 3 seconds, 3.5, and 4, like this. Take the time and substitute it in Vx. At time equal to 0, what is Vx? Oh, it's equal to this constant value. So at time equal to 0, constant. At time equal to 0.5, constant. At time equal to 1 will be constant. Time equal to 2, so this is always constant like this. So this will be our V naught cosine theta. How about the y direction? At time equal to 0, substitute it here. This will be 0, and you will get positive value for the V naught cosine sine theta. So assume the V naught is kind of located here. V naught sine theta located here. At time equal to 1.5, so you substitute 0.5 here. You see this is negative. Multiplied by t, so this will give you 0.5 g. And then this will be subtracted from V naught cosine theta. So what I expect is to get a value that is right here, almost. And then you substitute the time equal to 1. This will be minus gt. Again, it will be smaller value. And as you can see, this equation represents a straight line with negative slope. Starts with positive value, and the slope is going to go down. So if I plot this line, it will look something like this. Linear equation like this. How about the displacement? If I would like to plot the displacement, again I will do the same. I will have the horizontal x-axis representing the time. So I have, this is t, and this is the displacement, x of t and y of t. By the way, this value here is V naught sine theta. Now if you look at x, again I'm going to have the same time scale. So this is 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, and so on. If you look at this equation here, this is a line with certain slope based on the value of V naught and the cosine theta. Now this line starts from the origin because there is no constant added here. So if you draw this line, if the slope is positive, then it will be something like this. The displacement in the x direction is increasing with time in a linear manner. If you go to the second equation and try to plot this equation, this is a parabolic function. At time equal to 0, the value of the function is 0. So here is 0. If you increase the time, this function is going to increase faster than this at the beginning, and then this will increase faster than this. So you can see this is going to go like this, parabolic like this. This peak will depend on the value of V naught and will determine the value of V naught and the theta, which will determine where this peak is going to happen. So this will be y of t. If you build this model in atoms and run the simulation, basically the particle is going to behave like this. What do we mean by behave like this? If you plot the characteristics of the motion, which means displacement and the velocities should go like this. And this is actually what we would like to do. So now we have the equations, we have the expected results. We would like to analyze our model in atoms. We would like to build a virtual model in atoms and look at if this virtual model is going to behave as we expected. If you remember from last lecture, we said the analysis will go in 3 steps. The first step is, so the 3 steps in modeling and analyzing the model in virtual processing system is basically those 3 steps. The 3 steps are: number 1, pre-processing. In the pre-processing, we build our system. So we build the particle, we apply the forces acting on this particle, and whatever other things acting on the body, we define it. And then we run the simulation. And as we said before, when we run the simulation, the program or the solver is going to develop the list of mathematical equations according to the physics that we have in our problem. So those equations that we developed here are the mathematical equation describing our physics. If we have electrical system, it will be included. If we have fluid system, it will be included. If we have aerodynamic system, it will be included. If we have heat transfer, it will be included, and so on. So let me just give you an example of the aerodynamic. Remember the first assumption that we said in this particle? We are neglecting the drag force from the air. We are neglecting the resistance from the air. The resistance from the air will come as a drag force that will oppose the motion. So if the particle is moving in air, there will be a resistance. And this resistance is exactly what you feel if you are driving your car and you put your hand on the car, outside the window, you will feel the air is pushing you. This resistance also acts in any projectile. For simplicity and for our analysis, we are neglecting this. Why is that? Because this drag force is typically function of the velocity cubed. And if we include it in our simple analysis here, this forces, these equations that we get, those differential equations that we get, are simple because we are neglecting this drag force. If we include the drag force, it will give me nonlinear differential equation. Unfortunately, at your level right now, you don't have sufficient background in how to solve nonlinear differential equation. If you have a good solver, the good solver will allow you to include this type of forces. And when this type of forces will be included in your model, the solver is going to include it in the differential equations like this. So during the processing stage, the solver is going to include all the physics that is needed to run your simulation. After including all those equations, the solver is going to use mathematical tools to solve those equations. The equations that we have are simple, linear, second order differential equation. In actual systems, you might have partial differential equation, you might have linear system of equations, you might have linear system of equations and partial differential equation coupled together. We call it differential algebraic equation system. Or you might have more complicated partial differential with algebraic equations. In that case, the solver should be able to include those equations and solve them. So what do you mean by solving them? The solver will do exactly what we did here. The solver is going to assume the first initial step. It will take the initial conditions at this step with certain time step. So it will start from here to here. We know the system behavior at this point. When the projectile at the origin, we know everything about the projectile. We know the position, we know the velocity, the initial velocity, so we don't need anything else. But now we would like to know what is going to happen after 0.5 second. So the solver is going to take this time step, and it will use the initial conditions here and solve those differential equations. What do you mean by solving them? It will use the mathematical methods that you studied before, and it will determine the new velocity at this time, the new velocity right here, and the new displacements, and the new forces at the new time. And it will store those values in something like table. So it will say at time equal to 0, we knew everything. We used the solution from this step to go to the next step. What will happen next? Oh, now we would like to go to another time step. We would like to advance more. So we'll assume there is delta t, another delta t here, from here to here, another delta t from here to here. And we would like to compute the values at this new delta t. So what is going to happen? The solver is going to take the solution from this point and assume it will be the initial conditions to the new step right here. Oh, what do you mean initial condition? Remember, in this solution you need the initial velocity and the initial displacement. The solution at this step is going to serve as the initial condition to the next step. And again, it will use the mathematical tools to solve the differential equations and come up with the solution. So it will define the new values of the velocities, displacements, and forces if needed at the new position, at the new time. And then what? Then again it will repeat. It will continue doing this until the end time. What is the end time? This is how long you want this simulation to be computed. Once it reaches the end time, it will say, I'm done. It will tell you that it is done. It solved all the equations during the time required. So what is the result? I would like to see the results. You will go to the post-processing step. So in the post-processing, you can plot the results like this. You can animate the results. You can see how the system is moving. You can see the stresses and strains, deflections. You can see the heat distribution, how the heat is changing over time. All of those are post-processing steps. So those 3 steps, once you complete those 3 steps, you have completed your analysis. So what do we do next? Part of the post-processing is actually to create a report about your analysis, including the assumptions, the model description, the simulation parameters, and include the results. And this report is what you submit either for your graduation or for your designer, who can make decisions based on this design. Okay, so let me ask you this question here. If you think about this projectile, and we are assuming this x represents the horizontal x-axis, which is actually the ground, and this y represents the vertical y-axis, which actually the attitude above the ground. As you can see here, this is our projectile motion. What happened, if we would like to interpret this result, what we see here is that x is increasing with time, and y is going in this direction like this. Y starts from 0. Oh, what do you mean by y 0? It means at the ground level. And y is going to increase while x is increasing. Y increase while x is increasing means the projectile is going up and traveling in the x direction. So if you, instead of plotting the data against time, I would like to plot the projectile motion against x against y. So assume this is our ground X and this is our attitude Y. At time equal to 0, X and Y are zeros, like this. So the projectile is starting from here. X is increasing means the projectile is traveling along this axis. Y is increasing, it means the projectile is traveling in this axis, along this axis, like this, going up. If Y is decreasing, it means the projectile is going down. When Y is positive, it means we are above the ground. When Y is negative, it means we are below the ground. So if I would like to do this plot as Y against X, we know X is increasing all the way with time like this. But Y is this parabola. So as X is increasing, Y is increasing going up, and then it will start to fall down like this. And as you can see, Y become negative. What does it mean to you if Y becomes negative like this?
Yes.
What
Yes,
is going to happen if Y becomes negative? And
it
does it make sense? Does it make
Yes.
any sense to you?
Yes, doctor.
Assume you have a rubber ball and you are throwing this rubber ball on the ground. So it will act like this projectile, exactly like this projectile motion. Now, what will happen when it reaches the zero level, which means the ground level? What does happen to the ground, the ball, the rubber ball? The rubber ball will typically bounce back like this. And it will go again exactly the same, using the same physics. It will have certain initial condition, certain initial velocity, and certain initial position for the X and Y, and it will go again in parabolic motion. But the problem here, depending on the material of the ground and the material of your rubber, we will lose some energy. And if you remember the restitution coefficient also will determine how much energy you will lose here. Because we lose some energy, the initial velocity that will start from here will be less than the initial velocity that we have here. Because we lost some energy, the initial velocity, this V, will be less than the throwing velocity here. This will be V1. But again, the behavior of your projectile will be the same. So it will fly until it hits again. It will lose some energy and it will fly again, like this. Again, the velocity here is going to be less than the initial velocity here, because we lost some energy here. This bouncing up and down is also some kind of physics that we can explore. And this is exactly what we are going to do today. We are going to build a model for the ground and model the physics of this bouncing up and down. We will go in a step by step, try to follow those steps, and try to work with me. If you got any problem, just try to stop me and we'll work it together. So this is our welcome screen from Adams. In this welcome screen, we are going to start a new model. So I'm going to click on new model, and clicking this new model will bring this window, and this is where we create a new model. As we learned it before, the first thing to do is actually define the working directory. So I'm going to click on this icon. It's going to take me to our folder explorer. So I'm going to scroll down until I reach my root directory, and this is our folder that I used for this class. I think this is MA. I think it's this one. So this is our folder here, MA Spring 2020-21. I'm going to click on select folder. And remember where did I do this? I put it on the root of my directory. So I go to BC, the root is Windows or C, like this. And I will create a new folder like this. I created last time. And you can see the folder appears here. I will select the folder. Now as you can see, this folder here, this folder name contains only English characters. And we did this in order to avoid having non-English characters that can cause problems to my Adams. I will go back to the first line here and I will define my model name. I'm going to call this model Projectile 1. Projectile 1, those are two different things. And we agreed in order to separate them, we use underscore and then the second word. So we write the first word, underscore, the second word. We will keep the gravitational direction in the global -y, and I'm going to keep the units millimeter, kilogram, Newton second. Remember that. I will click OK. So it will open the new model for me. And as you can see, the model name appears in the top left corner right here. And we have all the tree is defined right here. Let me expand my screen so you can see what we are going to do. As we agreed, the projectile is defined by one particle. So for this one particle, I'm going to use a sphere. So if I click on this under bodies tab, I will go to the solids and I will create a sphere. If we click on this, it's going to ask me to create a new part. This is exactly what I want. I will create a new part. I will define the radius of this part. Because it's a sphere, I will need to define only the main radius of the sphere. I'm going to use 5 centimeters. And again, notice MATLAB Adams is assuming that we have units different from the default units. The default units is millimeter. So if you want to use centimeter, you need to specify the units here. I would like to use 5 centimeters radius. So I'm going to type override this 5 centimeter. If you don't include the units, it will be treated as millimeter. I would like to place this sphere at the origin. So if you move your cursor on the working screen, you will see the sphere is jumping between the grid points. If you would like to specify exactly where you would like to have this center is located, if it is not the origin, you can specify exactly where is it going to be located by right-clicking anywhere. If you right-click, it's going to open this event location window, and in this event location window you can specify exactly where you would like to place the center of the sphere. Again, you right-click anywhere, it will open the event location window. So I'm going to define the x, y, z coordinates of the origin of, or the center of our sphere, which is located at the origin. So I will have 0x, comma, 0y, comma, 0z. So I have 0, comma, 0, comma, 0. If you click apply, it will place the sphere at the origin. So now I have created our sphere. I don't need this location event, so I'm going to close it. Again, if we go under the bodies, if you expand the tree for the bodies, you will see we have created part 2. Part 2 is not a representative name, so make it a habit for you. When you create a part, rename it and give it a representative name. So here we have part 2. In order to rename, we have 2 methods. You can highlight the entity like this and then click on this entity. Now as you can see, the line is blinking, so you can overwrite it now. So I'm going to define this as projectile. So this is the projectile, and you need to hit enter in order to apply these changes. The other way to rename, if you right click and select rename, it will open this window for you. So you can, over here, you can put the new names that you wish and click OK. It will apply the new changes and close this window for you. Now this is our part, and as you can see here, there is plus sign. If you expand this plus sign, you will see things that are attached to this part. What are those things? As you can see, the first thing here is called graphics. So this graphics entity represents the spheres that we have created here. And then we have CM, and CM stands for center of mass, and marker 1. Now, for every body, the body can be represented kinematically without any graphics. But we include the graphics in order to improve the presentation, and sometimes in order to include the inertia of our bodies. By default, similar to the part, Adams is going to give every one of those entities a name. Ellipsoid is the general name for general shape for a sphere. The sphere is actually a special case of the ellipsoid. The ellipsoid is the shape that has 3 different axes or 3 different diameters. If those 3 different diameters are equal, it will contract to a sphere. If you would like to change the parameters of the ellipsoid, let's first change the name. So I'm going to call this ellipsoid a sphere. In order to change the name, again, you can click, it will blink, you can overwrite, or you can right click and select rename. So here I am going to change this, make it sphere. Click OK. You can see the sphere have changed. Now, as you can see, the sphere also, you can right click and there is modify. This modify is going to modify the properties of the sphere. We'll talk about this later on. Also, you can see marker 1. What is marker 1? For the graphics, it may require 1 or more markers to define the graphics. For example, the sphere, you need to define the center of the sphere. So this center of the sphere is defined by a marker. But we didn't create a marker. Adams automatically generated this marker and attached this marker to the center of the sphere. What do you mean by marker? Marker is actually a coordinate system. We learned the coordinate system before, consists of 3 perpendicular axes that can be defined by an origin and orientation. In general, for this sphere, this marker represents the center of our sphere, which right now will be located at the origin. The orientation of this marker, which is the rotation with respect to the global coordinate system, doesn't have to be reoriented because the sphere is actually symmetric around all the axes. You can also give the marker a name. You can change the marker a name. So you can make this name, you can call it sphere center. Okay. Now, in order to change the marker name, I will right click and choose rename. As you can see, again, you can change the marker name from here. So I'm going to call this sphere center. If you click apply, it will change the sphere marker 1 to a sphere center here. But I would like also, while we have this window open, I would like to show you something else. Now, our model is called Projectile 1. So this is our Projectile 1 as it appears here. This projectile contains bodies, and it contains connectors, joints. It contains motions. It contains forces, and so on. One of the bodies of our projectile model is called projectile. So this projectile is part of our model Projectile 1. Now, if you look at this object name, what do you see here is actually the model name at the beginning, and then dot. This dot means whatever comes after is belong to this model. So what we have right now is projectile body. So this projectile body is part of our Projectile 1 model, like this. Now, and then you see dot. This dot means we are going to talk about something that belongs to projectile. This thing is called sphere center. So if you look at this, under projectile, you have sphere, center of mass, and sphere center. So this sphere center, which is, as you can see, the icon appears as a marker, belong to the projectile, and the projectile belong to Projectile 1, which is our model. This is called the hierarchy. This sphere center is owned by this body. This sphere graphics is owned by this body. So whatever can need to be applied into this marker or this projectile is actually going to affect the projectile body. We will talk about the hierarchy later on in more details when we see other objects. But what you need to know is that whatever comes under projectile are owned by this part. Now I am done with the naming, so I'm going to click OK. So now what we did, we defined only our projectile particle. So this is the projectile particle that we wanted to create. We didn't define any initial velocity or mass, and those are very important for our model. So what we need to do next is to define the mass and the velocity, the initial velocity. Remember, the mass and the initial velocity are properties of the body itself. So if I would like to change the properties of this body, I select the projectile part. You cannot select the sphere because the sphere is just a graphics. You need to select the part. If you right click on the part, you can select modify. So from the tree, you can right click on the part and then select modify. It will open this window for you. This window is called modify body. So what do you see here? You see the body with the name, and then we have categories which says mass properties. These categories is what we are going to deal with right now. Now I'm going to show you another way of opening this window. So I'm going to close this window. If you right click on the part from the window, the working window right here, if you right click on the part, you see this short menu. In this short menu, it will display what we clicked on. So it displays the part which is projectile. And it tells you that under this projectile, we have ellipsoid sphere. So this is exactly what we already have in this tree. Now, you can move, you can point to any one of those. But notice, when you change what are you pointing at, the menu, this sub-menu is also changing. Now I would like to modify the part itself. So those are the characteristics that we can modify. So I'm going to right click on the part, select the part by the name, and click on modify. You will get this window again, modify body. So everyone will go to file and select save database. You will get this screen because this is our first time to save our model. It will say saving current database as projectile1.pem. I will say OK. So this is going to save the file that I have created into the folder that I created before. So if you go to your folder where your model is located, you will find the model is created in that folder. So this is my folder here, this PC, Windows MA Spring 2021, and this is the projectile 1, and as you can see it is just saved right now. Again, notice the extension of your file is .pen, stands for binary. You cannot read this file, you can open it only using Adams. So now we are going to look at how do we modify our projectile. So I'm going to click on the body or the part, right click and select modify. Make sure you are pointing to the projectile part and then click modify. The first characteristic or category that we have here is called mass properties. If you look at this pull down menu, you can have name and position, mass properties, position initial condition, velocity initial conditions, or ground part. Today we are going to work with mass properties and velocity initial conditions. If we start with the mass properties right here, you will say define mass by. Define mass by, and then you have options. So in those options, you can have user input. If you select user input, Adams is going to open this window for you. You can input the mass. You can input the mass moment of inertia around the different axes. You can have IXX, IYY, IZZ. So if you have those inertia properties for an existing body, you can enter them here and click apply. It will implement them. So you can say, for example, I have 1 kilogram and then I have 0.5 kilogram meter per second square, and this is 0.5 kilogram meter per second square, and this is 1 kilogram meter per second square. Click apply. Adams will take it from you. For now, we don't have this information, so we are going to ask Adams to compute those values for us. So not going to use user input now. What other options? You can use the geometry and the density. Okay? So if you know the density of your material, you can specify the density right here. Oh, what is the density? If you are assuming this projectile is made out of steel, then the density will be 7,800 kilogram meter cubed. But remember, for this model, we are using millimeter for the units. In that case, you need to convert the density from kilogram per cubed meter into kilogram per cubed millimeter. So you have to divide it by 10 to the minus 3 power 3, which is 10 to the minus 9. So you need to define your density according to the values and units that you are using. The other option which I would prefer is to use geometry and material type. What is this? Adams is going to compute the volume of your geometry, and then it will use the density of the materials and multiply it by the volume and compute the inertia properties based on this. So you can specify the material type. The geometry we already defined a sphere. I can define the material type here. By default, Adams is going to use steel. What if I would like to have different material? You can define your own material from here. If you remember, this icon allows you to define your own material. But Adams also have some built-in materials. How do I know those? I can place my cursor here and notice, right click, and here it says materials. If you have those materials saved, you can browse and get those materials, or you can select the guesses. So if you click on guesses, what you see here are some built-in materials in Adams. You can select the one that matches your need. So I'm going to assume I'm going to select aluminum, for example. If we start with aluminum, once you select the aluminum, Adams is going to load the built-in data for this material. Like what? Like density. And as you can see, this density is defined using the correct units. Adams is going to do the correct conversions for you. So this aluminum will have density equal to this value, kilogram millimeter cubed. Other properties that you will see, the Young's modulus, as you can see, Newton millimeter squared. And Poisson's ratio. Poisson's ratio, it is unitless. So you don't have any units for Poisson's ratio. So now I selected the aluminum as our initial, material. I would like Adams to use this and calculate the values of the inertia. So I will click apply. Once we click apply, it's already done. So Adams computed the volume, multiplied it by this density, and computed the mass and the inertia. How do I know the mass of our object? You click on show inertia, show calculated inertia, and these are the values right here. As you can see, the mass of this object is 1.434 kilogram. The moment of inertia around X is 1434 kilogram millimeter squared, and so on. So now we have created the mass and the inertia of our part, and this is very important. If you don't have mass in your system, then go back to the equations. If the mass is not defined, if the mass is 0, then you divide this equation by the mass, you will get x double dot is equal to infinity, and this will cause problem to your Adams model. So every part in your model has to have mass and inertia. Also, notice if we go under all others, if you look at this item here in the tree and expand it, you will see materials. If you expand it again, you will see the steel that is already loaded by atoms by default and the aluminum that we selected to add in our model. So now we defined the mass of our particle. I would like to give this particle initial velocity. Oh, how much initial velocity? Assume I would like to give this particle V naught. So I'm going to do an example here. V naught is actually 5 meters per second, and I'm going to fire this object at angle 45 degrees. So if I fire this object at 45 degrees, what would be the initial velocity in the x direction and the initial velocity in the y direction? In this case, I can write V naught x is equal to 5 cosine 45 degrees, and V naught y is equal to 5 sine 45 degrees. So I can calculate those values. If you would like to calculate those values, you will multiply 5 times sine 45 degrees. Yes, sir. So we'll have
Doctor,
So I would like to calculate the initial velocity in the x and y direction. They are going to be exactly the same because the sine is equal to the cosine of 45 degrees. If we compute this velocity, it will be 3.535 millimeter per second in both directions. So we'll input our initial velocity 3.535 meter per second, in x 3.535 meter per second in the y. So those are the values that we would like to use in our initial. The next step is to input the initial velocity in the x and y direction. How do I do that? We'll go under category and click on the drop down menu and go to this initial velocity initial conditions. If you click on velocity initial conditions, you can see we have, for any body, you will have translational velocity and rotational velocity. And you can define those initial velocities independent from each other. If your body has initial displacement only, initial translation only, translational velocity only, or initial rotational velocities only, you can select which values you would like to define, as you can see here. And also you can define the reference. What is the reference of your velocity? You can define that velocity relative to the ground, the global coordinate system, or relative to a specific marker, and you can select this marker. We'll talk about this in other examples. So we're going to assume our body will have initial velocity relative to the ground, and this is actually exactly what we have. The initial velocities are defined in the x-axis direction, so I will click on this, check this box, and in the y direction, I don't have initial velocity in z or initial rotational velocity, so this is what I need only. How much was the initial velocity that we have? We computed it 3.535 meter per second. So here we enter our initial velocity, but remember what units we used? We used millimeter. So I have to write down my velocity in millimeter per second. So it will be 3.535 meter per second. The same for y, 3535. This is the value that we calculated here. Or if you would like to enter with units, so if you would like to enter this with units, you can have 3.535, and then you enter meter per second and close the parentheses. So if you enter it as millimeter per second, or you enter it as meter per second, both of them will work. So now I have those velocities in millimeter per second, and this is all what I needed for this body properties. So I will click OK. Now at this point we have defined our particle with the initial conditions. As a matter of fact, we done all what is needed, because we have the gravity is already defined. How do I know the gravity? The gravity is a force. So you go under forces, you will see the gravity is right here. If you would like to check the value of the gravity, again right click and choose modify. You can see the gravity is defined in the negative y direction like this, and it's also defined in millimeter per second, 9,806.765 millimeter per second. So this will be consistent with our model units. So I'm going to close this again. At this point we are ready to run our simulation. So assume we would like to run this simulation for say 5 seconds. How do I run the simulation? We go under this tab, the simulation tab, and click on this interactive simulation. Now I will click on this button without any changes, and then I will explain the parameters that we need to change here. Just to check if the model is working, click on this button. Adams right now have created the equations and solved those equations for us. Because it's running fast, we were not able to follow up where this object flying. Assume your model didn't have a gravity, or you forgot to add the gravity, or by mistake you deleted the gravity from your model. How can I get it back? I can get the gravity back from settings. If we click on settings, you will see this drop down menu, and then you can select the gravity right here. Click on gravity, you will get this gravity settings window. In this gravity settings window, the first thing that you need to check is this checkbox. If it is hidden, if it is checked or unchecked, make sure this gravity checkbox is checked. If it's checked like that, it means we are going to use the gravity in our model. If you uncheck it like this, there will be no gravity in our model. This projectile will have the parabolic motion when we have the gravity acting on it. So I will check this gravity, which direction your gravity is acting. If you, depending on the model that you are building, for our model the gravity is acting in the negative y like this, and depending on the position on earth, where you are on the earth, this value can be different. So you, depending on what simulation you are doing, you can select the value of your gravity and include it here. So if you don't have this in your model, please make sure the gravity is activated, and this value is for units systems that use millimeters for the length. Once you enter the values, click OK. Once you click OK, it should appear, the gravity should appear under forces like this. Let's go back to our this interactive simulation window and see what we have. As we have learned before, this button is to run the simulation or start the simulation. See, when you move your cursor in the top of the button, it will give you this tooltip, and also in the status bar right here, it tells you what is the button is doing. So when we move our cursor here, it says start the simulation. And this one is to stop the simulation. If the simulation is running and you see things are not going correct, or the simulation is taking too much time, you can stop the simulation. If you run one simulation and you would like to rerun it again, you need to reset the system to the initial configuration. So this button is to reset your system to the initial configuration. So here we have reset, stop, and start. Oh, what are those? This is going to redo the same simulation, and this one is very nice feature that we always forget, and this feature is actually to check the model. So if you click on this button right here, it's going to go over your model and all the joints that you have. It will check if there is any redundancy, and also it's going to check how many degrees of freedom you have in this system. And as you can see here, we have a summary. As you can see, it says Gerbeler count approximately 6 degrees of freedom. Why do we have 6 degrees of freedom? Because we have one particle in space, it has 6 degrees of freedom. No joints yet, so this body is going to have freedom to move in X, Y, Z, rotate around X, Y, and Z. That's why you can see the Gerbeler criteria, or the mobility index, is 6. And it tells you how many parts you have in the model. So we have one moving part. This moving part is this particle. Or how about the ground? As you can see, it says not including the ground. The ground is just there, you like it or not. And then it will give you a summary right here, and it says your model is verified successfully, which means your model is good to go. I will close this window, and again this window to check the mobility index and the system consistency is verify window. The second line here, it says end time, which means Adams is going to run the simulation from the time 0, or the initial time, until 5. And if you remember, we used second for the time, so it will run it for 5 seconds. But notice also we have this drop down menu. What is it? What other options? It's going to say duration. So you would like to run the system for 5 seconds, or you would like to run the system forever. So this is going to run the model until you stop it, and that's why you have this stop button. If you run forever, sometimes you don't want, you are looking for some events to happen and you don't know when this event is going to happen, so you choose run forever. Once you see the event is happening, you can stop the simulation. For most of our simulations right now, we are going to use this end time, and I'm going to run it only for 2 seconds. So I'm going to change this to 2. Now, what is steps? Remember when we talked about the solution right here, we said Adams is going to run from the initial time until the final time. And in order to go from the initial to the final, it's going through steps. So now You can specify how many steps you would like to Adams to perform the simulation from the beginning till the end. By default, Adams is going to have 50 steps. So what does it mean? It means Adams is going to take between 0 and 2 seconds 50 steps. So what will be this delta t? You take 2 seconds divided by 50, so delta t is equal to the final time, which is 2 seconds, divided by the number of steps. It will give you 0.04 second. So from here to here, Adams is going to take 0.04 seconds, and the result will contain this 50 output points that we specified. Sometimes we don't want to specify the number of steps. Sometimes we would like to specify the delta t by itself. So instead of specifying the number of steps, I would like to specify delta t. Adams also allows you to specify the step size. So assume I would like to use 0.01 second. You can select step size and select 0.01 second, like this. Now how many steps are we going to have? See, if we have delta t equal to 0.01 second, and this will be equal to the final time divided by n steps. This means our n is going to be equal to 200 steps. So what is 200 steps means? Again, it will be the number of calculations done between the initial and the final points. So again, what is going to happen at time equal to 0? Adams assume it will have the initial conditions, so it will take an increment of delta t, this delta t that we have, or the specified delta t, and then it will solve those differential equations using the new delta t. How is it solved? You learn it in the numerical methods how those differential equations will be solved, and then it will compute the states, displacement, velocity, forces, and everything will be calculated at new delta t. Those states are going to be used as the initial condition for the new step. So Adams is going to advance a new delta t using those states as the initial conditions for the next stage, advanced by delta t, and so on. Which means in our case here, Adams is going to solve those differential equations 200 times. This would require processing from your computer. Depending on the power of your computer, this processing may take long CPU time or short CPU time. So determining the step size and the number of steps will be very important for you in order to determine the simulation time, how long Adams is going to take to run your simulation. So assume I have the end time is 2 seconds, delta t, the step size is 0.01 second. I can run this simulation. So if I click on the start simulation, you will see Adams created the equation, solved the equation, and our system, our object actually is flying. We don't know where. So in order to look where this object is flying, we can zoom out on our system. So I can translate my system down here and zoom out. To remind you, in order to zoom out, I will click on this magnifier and drag the left button. Click on the left button and drag it. As you can see, it will make the system smaller. Now I will drag this to the bottom left corner. In order to drag, I will click on this hand, and then I will click on the left button and drag the model to this end like this. I would like to run this simulation. We already run it, right? So I would like to rerun it. In order to rerun it, I have to reset the system to the original configuration. So I will click on this button. Our system now is reset. I will click play, and as you can see, it's falling down. So now I can say my screen is too small, so I can magnify it again. So I can zoom out a little bit, zoom in a little bit, and move it to the middle of the screen so you can see the model better. Reset again and run. So now, as you can see, this is what we expected from our model. Our model is flying. Our model is flying up and then falling down. Flying up and then falling down until it reaches very far distance. So this will be last time. Right click on the particle, select the part, click on measure. It will open this window for you. I am going to call the name Y displacement, and then I am going to component. I would like to look at the Y component. Click on it and then click OK. Once you click OK, it's going to generate this strip chart for you, and you can see the displacement is increasing in the Y positive direction, and then it will go to 2. I'm going to change my end time to 1 second, and then reset the configuration. Run the model. As you can see, it is flying up and falling down. While it is doing this, the measure is updating. Now you can see the displacement in the Y direction against the time. You can see under measures, we have the Y displacement is already created here.